Welcome to white space. Can a dead star 50,000 light years away still reach Earth? Put this on in the background, close your eyes if you want, and let the story carry you. There are moments in the life of our civilization when we become acutely aware of how narrow the window of our direct experience really is. We are bound to the surface of one planet, orbiting one star in one corner of a galaxy that itself sits in one of billions of galaxy clusters scattered across a universe so vast that even light, the fastest thing we know of, would take billions of years to cross it. And yet here we are, curious, restless, and unwilling to accept the limits of what we can reach with our hands. Over the last century, our instruments have grown into extensions of that restlessness, telescopes the size of stadiums, probes drifting in silence billions of kilometers from home, spectrometers that can read the chemistry of a planet's atmosphere without ever leaving our own. These tools have transformed our picture of the cosmos from something vague and mythological into something specific and astonishing. The universe, it turns out, is not just vast. It is strange, stranger than most people know, and stranger still than most textbooks say. So let us take a journey, not in a rocket, not yet, but in the way humans have always traveled before the technology catches up, in imagination, guided by data. We will visit objects that challenge our intuitions about what matter can do, what stars can become, and what waits at the edge of everything we can see. We will begin at the far end of our own solar system and move outward, step by step, into the deep. Our first destination lies 3 times farther from the Sun than Pluto. It is a world covered in frozen methane, eerily red and alone in one of the most inhospitable stretches of space our solar system has to offer. Its name is Eris. When Eris was first detected on January 5, 2005, by astronomers Mike Brown, Chad Trujillo, and David Rabinowitz at the Palomar Observatory in California, it caused what could fairly be called a crisis in planetary science. At first, the object appeared to be larger than Pluto. The discovery immediately raised a question that the astronomical community had been quietly avoiding for years. If Pluto counts as a planet, what exactly do we do with this? The answer arrived in 2006 at the International Astronomical Union's General Assembly in Prague was to recategorize both Pluto and Eris as dwarf planets, a new formal classification for objects that orbit the Sun and are massive enough to be roughly spherical, but have not gravitationally cleared their orbital neighborhoods of other debris. Eris has a diameter of approximately 2,326 kilometers, making it only marginally smaller than Pluto, whose diameter measures around 2,377 kilometers. The difference is so small that for years after the discovery, scientists genuinely debated which of the two was larger. It was only the New Horizons mission flyby in 2015 that provided precise enough measurements to settle the question in Pluto's favor. Despite being slightly smaller in volume, Eris is considerably denser and more massive than Pluto. Its mass is approximately 1.66 times that of Pluto, making it the most massive known dwarf planet in the solar system. Eris orbits the Sun on a highly elliptical path that takes it from about 38 astronomical units at its closest point to nearly 97 astronomical units at its farthest. 1 astronomical unit is the average distance from Earth to the Sun, approximately 150 million kilometers. At its most distant, Eris is nearly 14.5 billion kilometers from the Sun. Its orbital period around the Sun takes approximately 559 Earth years to complete. When Eris was discovered, it was close to the most distant point of its orbit, which is one reason it had escaped notice for so long despite its considerable size. The surface of Eris is among the brightest in the solar system, reflecting approximately 96% of the sunlight that hits it. By comparison, fresh snow on Earth reflects around 80%. This extraordinary reflectivity is thought to be the result of a thin layer of nitrogen ice that continuously refreezes onto the surface as Eris moves away from the Sun. When it travels closer to the Sun during its elliptical orbit, this nitrogen ice slowly sublimes, transitions directly from solid to gas, forming a thin temporary atmosphere. As the dwarf planet recedes and temperatures fall again, that nitrogen recondenses and coats the surface in a fresh white frost. The cycle repeats every 5.5 centuries. What lies beneath this bright surface crust is harder to determine. Spectroscopic analysis suggests the presence of methane ice, which is responsible for giving Eris a faint reddish tint in some observations. This is broadly similar to Pluto and points to a shared history of formation from the cold outer reaches of the solar system's primordial disk. Eris has one confirmed moon discovered in 2005 and officially named Dysnomia in 2006. The name is fitting. In Greek mythology, Dysnomia is the daughter of Eris, goddess of discord, and is associated with lawlessness. Dysnomia is approximately 700 kilometers in diameter and orbits Eris roughly every 15.8 days at a distance of around 37,300 kilometers. The Moon's relatively circular orbit and the way it interacts gravitationally with its parent body have allowed scientists to calculate Eris's mass with reasonable accuracy. Eris is classified as a scattered disk object, meaning its orbit was likely shaped by gravitational interactions with Neptune in the distant past, scattering it into its current highly elliptical trajectory. This makes Eris a kind of relic of the solar system's dynamic early history, a frozen record of collisions, migrations, and gravitational chaos that played out over billions of years. From Eris, we travel deeper still into a region of space that confounds even the most experienced planetary scientists. The object we are looking for is not on any standard chart of the solar system. It lies so far from the Sun that sunlight takes more than 20 hours to reach it at its closest approach, and nearly 3.5 days when it is at its most distant. This is Sedna, discovered on November 14, 2003. By the same team responsible for finding Eris, Brown, Trujillo, and Rabinowitz. Sedna immediately defied classification. Its orbit carries it from approximately 76 astronomical units at perihelion to an extraordinary 937 astronomical units at aphelion. At its farthest point, Sedna is nearly 140 billion kilometers from the Sun. Its orbital period is estimated at roughly 11,400 years. These are numbers that strain comprehension. For context, the Voyager 1 probe, launched in 1977 and currently the most distant human-made object in space, has traveled a little over 23 astronomical units per decade. At that rate, it would take Voyager 1 roughly 4 centuries just to reach Sedna's closest approach to the Sun, if the probe were heading in that direction. Sedna's diameter is estimated at approximately 995 kilometers, making it somewhat smaller than Eris, and it is considered a strong candidate for dwarf planet status, though it has not yet been officially classified as one. What makes Sedna particularly extraordinary is not its size but its orbital characteristics. Nothing in the established dynamical models of the solar system satisfactorily explains why an object would have such an extremely elliptical orbit reaching so far from the Sun. In the standard picture, the solar system's outer boundary is defined by the Kuiper belt, which extends to roughly 50 astronomical units. Beyond that lies the hypothetical Oort cloud, a vast spherical halo of icy bodies thought to be the source of long-period comets. Sedna sits in the gap between these two regions, too far to be a Kuiper belt object, too close to be part of the classical Oort cloud. Several hypotheses have been proposed to explain this anomaly. One suggests that Sedna was gravitationally disturbed by a passing star in the early solar system, which would have stretched its orbit into its current extreme shape. Another proposes that Sedna was captured from another stellar system during the Sun's formation in a dense stellar cluster. A third and more controversial hypothesis has gained traction in recent years, that Sedna's orbit, along with several other similarly anomalous trans-Neptunian objects, bears the gravitational fingerprint of an as-yet undetected planet lurking in the outer solar system. This hypothetical object, sometimes called Planet 9, would need to be roughly 10 times the mass of Earth and orbit at hundreds of astronomical units to produce the clustering patterns observed in extreme trans-Neptunian objects like Sedna. To date, no direct evidence of such a planet has been confirmed. Sedna's surface is one of the reddest in the solar system, second only to the moon of Mars, called Phobos in some measurements. The reddish hue is thought to result from the presence of tholins, complex organic molecules formed when simple carbon-bearing compounds like methane and ethane are irradiated by cosmic rays and ultraviolet light over billions of years. These same compounds have been found on Pluto, on the moon Triton, and in the atmospheres of outer solar system bodies. They represent a kind of slow chemistry happening in the cold and dark, driven not by heat but by radiation. The surface temperature on Sedna is among the lowest of any known object in the solar system, estimated at approximately minus 240 degrees Celsius, only 33 degrees above absolute zero. At these temperatures, chemical reactions slow to a near standstill. What Sedna preserves on its surface may be some of the most pristine material in the solar system, virtually unchanged, since the era of planet formation over 4 billion years ago. One confirmed companion, similar to the moon discovered alongside Orcus or Eris, has not been found for Sedna. This absence is itself informative. Objects as large as Sedna that do have moons typically acquired them through collisions during the solar system's early history. When collisions between large bodies were far more common, Sedna's apparent solitude in this regard may hint at its origin in the region of space where encounters between large bodies were rare, which would be consistent with its proposed formation in an outer fringe of the primordial solar nebula. Sedna will not return to its current position near the Sun for another 11,000 years. Any probe sent to intercept it would need to launch within the next few decades to take advantage of this proximity. Several mission concept studies have explored this possibility. A flyby mission to Sedna, if it were launched in the 2030s, could reach the object by the 2070s using gravitational assist maneuvers from Jupiter and Saturn. The scientific return could be enormous. A direct sample of material from the outermost edge of our solar system's formation zone, unchanged since before the Earth existed. Having reached the outer limits of our own solar system, we now turn to a question that every generation since the invention of the telescope has asked in some form: how would we ever cross the distances between stars? The nearest stellar system to our own, Alpha Centauri, is 4.24 light-years away. That is approximately 40 trillion kilometers. The fastest spacecraft humanity has ever launched. The Parker Solar Probe reaches speeds of around 700,000 kilometers per hour at its closest approach to the Sun. At that speed, a journey to Alpha Centauri would take approximately 6,500 years. Clearly, conventional chemical rockets, even the most powerful we can imagine, are fundamentally unsuited to interstellar travel. The problem is not simply one of speed, it is one of energy. Chemical propulsion works by releasing the energy stored in molecular bonds. This is an efficient way to release energy relative to the mass of the fuel when operating within a planet's gravitational field. But it is extraordinarily inefficient when compared to the distances and speeds involved in interstellar travel. The ratio of energy to mass in chemical fuels is simply too low. One concept that has moved from pure science fiction into genuine engineering research over the past few decades is the laser-driven sail. The basic principle involves accelerating a very lightweight spacecraft by shining a powerful laser beam onto a reflective sail. Because the spacecraft itself carries no propellant, it can potentially be accelerated to a significant fraction of the speed of light, perhaps 5 or even 20%, using enough laser power. At 20% the speed of light, a probe could reach the Alpha Centauri system in approximately 20 years. The Breakthrough Starshot project, announced in 2016 and backed by significant funding from private technology investors, has taken this concept seriously as an engineering challenge. The proposal involves launching gram-scale spacecraft, essentially tiny chips carrying cameras, sensors, and communication equipment attached to square meter sails, and accelerating them with a phased array of ground-based lasers, producing a combined power of around 100 gigawatts. The challenges are considerable. The lasers would need to maintain focus across interstellar distances. The spacecraft would need to survive impacts from interstellar dust particles at relativistic speeds, and any data returned from the target system would take over 4 years just to reach Earth at the speed of light. Nevertheless, the fundamental physics does not prohibit this approach. It does not violate any known law of nature. What it requires is engineering at a scale humanity has not yet achieved, but could, in principle, achieve. An alternative approach that addresses slightly shorter distances, travel within our own solar system on faster timescales, is nuclear pulse propulsion. The concept, studied seriously in the late 1950s and 1960s under the code name Project Orion, proposed detonating a series of small nuclear explosives behind a spacecraft and absorbing the resulting blast pressure through a pusher plate and shock absorbers. The theoretical calculations suggested that a spacecraft using this method could achieve exhaust velocities of several thousand kilometers per second, orders of magnitude faster than any chemical rocket. Project Orion was eventually shelved for political and treaty reasons, but the engineering studies produced in that era are still consulted by researchers exploring advanced propulsion today. A more refined nuclear option that has returned to serious discussion is the nuclear thermal rocket. Unlike nuclear pulse propulsion, this approach uses a nuclear reactor to heat a propellant, typically liquid hydrogen, to extremely high temperatures, producing much higher exhaust velocities than chemical combustion can achieve. NASA and the Department of Defense have actively funded development contracts for nuclear thermal propulsion in the 2020s, with the aim of demonstrating a working engine within this decade. Such an engine could reduce transit times to Mars from 6 to 9 months down to roughly 3 months under favorable orbital conditions, and could eventually serve as the propulsion basis for crewed missions to the outer solar system. Beyond these, researchers have also explored the concept of fusion propulsion, using the same process that powers stars to drive spacecraft. In fusion, light atomic nuclei are forced together at extremely high temperatures to form heavier nuclei, releasing energy in the process. A spacecraft using a fusion drive could theoretically achieve exhaust velocities of several % of the speed of light, making it the most plausible technology for travel to nearby stellar systems that does not require exotic physics. Several private companies and research institutions are currently working on compact fusion reactor designs, though a commercially viable fusion power plant remains an elusive goal. Whether any of these technologies will ultimately be realized depends on choices that have not yet been made, funding decisions, political will, and the unpredictable trajectory of scientific discovery. But the physics at least points toward possibility rather than impossibility. Now, let us visit one of the most remarkable star systems in the known universe, one that has drawn the attention of astronomers for decades precisely because it seems to operate at the limit of what physics allows for stellar systems. Nu Scorpii lies approximately 470 light-years from Earth in the constellation Scorpius. To the naked eye, it appears as a single star of modest brightness. A good pair of binoculars resolves it into two distinct objects. A telescope reveals more, and careful spectroscopic analysis over many decades has uncovered the full picture. Nu Scorpii is a system of at least 7 stars. The 7 components are arranged in 2 gravitationally bound subgroups separated by a projected distance of approximately 41,000 astronomical units, about 2/3 of a light year. The first subgroup contains 4 stars. Nu Scorpii A and Nu Scorpii B are a tight binary pair orbiting each other with a period of just over 1.9 days, meaning each completes a full orbit around the other in less than 2 Earth days. Nu Scorpii AC orbits this inner pair at a greater distance, and Nu Scorpii AD itself, a spectroscopic binary, adds a 4th and 5th component to this group. The second subgroup, approximately 41,000 astronomical units away, consists of 2 additional stars, Nu Scorpii E and F, which orbit each other and are gravitationally bound to the rest of the system. All of the stars in Nu Scorpii E are hot luminous objects classified as B-type main sequence stars or subgiants. They burn at temperatures between roughly 15,000 and 30,000 kelvins, emitting intensely blue-white light. Their masses range from approximately 5 to 15 times that of our Sun. These are short-lived stars by cosmic standards. A star with 10 times the mass of the Sun burns through its hydrogen fuel at a much faster rate than a star like our Sun and will last only tens of millions of years before exhausting its core fuel and undergoing dramatic changes, potentially ending in a supernova explosion. The question of how a system with 7 gravitationally bound stars came to form is one that astronomers do not yet answer with complete confidence. The most widely accepted model holds that most multiple star systems form from the same cloud of molecular gas that gives rise to star clusters. When a cloud of gas and dust begins to collapse under its own gravity, it does not necessarily collapse smoothly to a single point. Turbulence, rotation, and density variations within the cloud can cause it to fragment into several collapsing cores simultaneously, each of which may independently form a star or small stellar binary. If these cores are close enough together, the stars they produce will remain gravitationally bound to one another. In the case of Nu Scorpii, the evidence strongly supports the hypothesis that all 7 stars formed from the same parent cloud at approximately the same time, roughly 3 to 5 million years ago. For any hypothetical planet that might orbit within the Nu Scorpii system, the conditions would be extraordinary. The sky would never be fully dark. Depending on the planet's position and orbital parameters, 1 or more stars would be above the horizon at nearly all times, bathing the surface in light of various hues. The concept of a night sky as we experience it, a dark vault scattered with distant stars, would be entirely alien to any hypothetical inhabitant. Instead, there would be a complex interplay of multiple illumination sources, shifting shadows, and rapidly changing lighting conditions as the nearby stellar companions moved through their tight orbits. At the same time, the intense ultraviolet radiation from the blue-white stellar components would pose severe challenges to the development of complex chemistry on any planetary surface. The same radiation that gives blue stars their color is extremely energetic and capable of breaking apart the molecular bonds that form the building blocks of organic chemistry. Life, as we understand it, would find it very difficult to gain a foothold under such conditions, at least on the surface. Weather-protected environments, deep oceans, underground layers, or highly shielded surface chemistry could provide the necessary conditions remains an open question. From Nu Scorpii, we now travel to something that cannot be called a star system in any conventional sense, because it is a single star so massive, so luminous, and so extreme in its properties that it occupies a category almost by itself. In the heart of the R136 star cluster, buried deep within the Tarantula Nebula in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, approximately 160,000 light-years from Earth, lies an object known as R136A1. By current measurements, R136A1 is the most massive star ever confirmed to exist. Its mass has been estimated at approximately 215 solar masses, though earlier estimates suggested it might be as high as 315 solar masses. This uncertainty arises from the extreme difficulty of observing individual stars within the densely crowded R136 cluster, which requires the resolving power of space-based telescopes or adaptive optics systems on the largest ground-based telescopes, regardless of the precise value. R136A1 sits at or very near the upper theoretical limit of stellar mass. This limit, sometimes called the Eddington limit, in relation to the pressure balance between radiation and gravity, represents the point at which the outward pressure of a star's own emitted radiation becomes strong enough to overcome gravity and prevent further mass accumulation. Estimates for where this limit lies vary depending on modeling assumptions, but most place it somewhere between 150 and 300 solar masses. R136A1's luminosity is staggering. It emits approximately 8.7 million times as much light as our Sun. To put that in perspective, if you were to replace our Sun with R136A1 at the same distance, its surface would appear in our sky as a disk roughly 100 times the angular diameter of the Sun. Daytime temperatures on Earth would be catastrophic. The planetary surface would be scorched to bare rock within geological instants. The star's surface temperature is approximately 46,000 kelvins, more than 7 times the surface temperature of our Sun. This extreme heat means that most of R136A1's energy is emitted not in visible light but in the far ultraviolet range, invisible to human eyes. The visible light we see from it is only a fraction of its total output. Objects of this mass do not live long. R136A1 is estimated to be roughly 1 to 2 million years old, barely a moment on cosmic time scales. Its main sequence lifetime will almost certainly be under 2 million years in total. For comparison, our Sun has been burning for approximately 4.6 billion years and is expected to remain on the main sequence for another 5 to 6 billion years. The lifetime of R136A1 relative to the Sun is roughly what a single day is to a century. When R136A1 finally exhausts its core hydrogen, its evolution will be rapid and violent. Stars of this mass do not quietly become white dwarfs. Instead, they are expected to pass through a stage as a luminous blue variable, an unstable giant prone to enormous outbursts that shed mass at extraordinary rates. Some portion of the star's mass is expelled into surrounding space through these events. Eventually, what remains either continues evolving into a Wolf-Rayet star, a type characterized by extremely high temperatures and ferocious stellar winds, or collapses directly in a catastrophic supernova or hypernova event. The remnant of such an explosion would most likely be a black hole. In the meantime, the stellar wind from R136A1, the constant stream of particles blown outward from its surface, carries away matter at the rate of approximately 1 solar mass every few tens of thousands of years. This wind is so powerful that it has already significantly reduced the star's mass from whatever it was at formation. The gas and dust around R136A1 have been sculpted by this wind into complex structures visible in deep images of the Tarantula Nebula. The region is one of the most active star-forming environments known, producing stars at a remarkable rate across a span of several hundred light-years. We have now visited worlds on the edge of our solar system and stars at the extremes of mass and luminosity. But the universe reserves some of its most peculiar behaviors for objects that have already completed their stellar lives, or more precisely, For what is left behind when those lives end in violence? When a star with a mass between roughly 8 and 20 solar masses reaches the end of its main sequence life, it does not simply fade. Its core collapses on a timescale of fractions of a second faster than any conventional object can fall. The outer layers of the star, no longer supported against gravity by the energy of fusion, fall inward and then bounce off the suddenly rigid inner core in a catastrophic rebound. The result is a supernova explosion, one of the most energetic events in the known universe, briefly outshining entire galaxies. What remains at the center of this explosion is a neutron star. A neutron star is the compressed remnant of the stellar core, packed to a density so extreme that the laws of physics begin to behave in ways that have no analogy in everyday experience. A typical neutron star contains between 1 and 2 solar masses of material compressed into a sphere roughly 20 kilometers in diameter. To arrive at this number by analogy, imagine taking the mass of approximately 500,000 Earths and compressing it into a ball the size of a medium-sized city. At these densities, the electrons that normally orbit the nuclei of atoms are forced by gravity to combine with protons, forming neutrons. The result is a star made almost entirely of neutrons, packed together so tightly that a teaspoon of neutron star material would weigh approximately 4 billion tons on the surface of Earth. The discovery of neutron stars came in a form that nobody anticipated. In 1967, British postgraduate student Jocelyn Bell, working under astronomer Anthony Hewish at the Mullard Radio Astronomy Observatory in Cambridge, detected a highly regular radio signal pulsing every 1.33 seconds. The signal was so precise and regular that for a brief period the team internally designated it LGM-1 for Little Green Men, half-jokingly considering the possibility of an artificial origin. It was quickly recognized as a natural phenomenon, a rotating neutron star whose magnetic field channels radiation into a narrow beam, sweeping across the sky like a lighthouse as the star rotates. Objects of this type are now called pulsars. Pulsars can rotate with extraordinary speed. The fastest known, called millisecond pulsars, complete hundreds of full rotations per second. The current record holder, PSR J1748.2446 AD, rotates 716 times per second. At its equator, the surface is moving at approximately 24% of the speed of light. The centrifugal force at the surface of such an object would be enormous, yet the extreme gravitational field of the neutron star keeps the material bound. Pulsars are also extraordinary clocks. Their rotational stability rivals the best atomic clocks ever built, and arrays of millisecond pulsars have been used as gravitational wave detectors, sensitive to the ultra-low frequency ripples in spacetime produced by merging supermassive black holes at the centers of distant galaxies. An even more extreme class of neutron star exists, the magnetar. Magnetars possess magnetic fields estimated at between 10 to the power of 14 and 10 to the power of 15 Gauss. That is approximately a quadrillion times stronger than the Earth's magnetic field. For comparison, a typical refrigerator magnet operates at around 100 Gauss. At these field strengths, the magnetar surface is subject to periodic quakes, sudden rearrangements of the crust driven by the extreme magnetic stress that release enormous amounts of energy in the form of gamma-ray flares. On December 27, 2004, a gamma-ray flare from a magnetar called SGR 180620, located approximately 50,000 light-years away, was detected by instruments in orbit. Despite the vast distance, the flare briefly ionized the upper layers of Earth's atmosphere. Had the magnetar been a few light-years closer, the event could have been catastrophic for the biosphere. To date, fewer than 30 magnetars have been confirmed in the Milky Way, though more are presumed to exist in regions where they have not yet been detected. Their lives as highly active magnetars are short. The extreme magnetic fields decay over thousands of years. after which they quiet down and become indistinguishable from ordinary neutron stars. The study of neutron stars and magnetars has offered some of the most stringent tests of physics under extreme conditions that are simply impossible to recreate in any laboratory on Earth. The behavior of matter at nuclear and supranuclear densities, the physics of extremely strong magnetic fields, and the dynamics of relativistic rotation, all of these can be studied through observations of these objects in ways that cannot be replicated by particle accelerators or any other instrument of our own making. And yet even neutron stars are not the most extreme endpoint of stellar evolution. When a star with a mass exceeding roughly 20 to 30 solar masses reaches the end of its life, or when two neutron stars merge, or in various other extreme scenarios, gravity wins completely. The remnant core collapses not to neutron star density, but beyond past any known form of matter into a singularity, a point of infinite density around which space-time is so severely warped that not even light can escape. This is a black hole. The boundary at which escape becomes impossible is called the event horizon. It is not a physical surface, but a mathematical boundary, a limit in the geometry of space-time. Once anything crosses this boundary, the future it leads to contains only the singularity. There is no exit. Black holes of stellar mass range from roughly 3 solar masses, the minimum possible, just above the maximum for a neutron star, to tens or even hundreds of solar masses for the remnants of the most massive stars. But there is another class entirely, supermassive black holes found at the centers of virtually every large galaxy. These range from millions to billions of solar masses. The supermassive black hole at the center of our own Milky Way, designated Sagittarius A, has a mass of approximately 4 million solar masses. The first direct image of a black hole's shadow, the region of darkness surrounding the event horizon, was captured by the Event Horizon Telescope collaboration in 2019, showing the supermassive black hole at the center of the galaxy M87, some 53 million light-years away, and mass of approximately 6.5 billion solar masses. The formation of supermassive black holes remains one of the major unsolved problems in astrophysics. They could not have grown to their current sizes simply by accreting material at observed rates since the Big Bang. Observations with the James Webb Space Telescope, launched in 2021 and beginning full science operations in 2022, have revealed supermassive black holes already in place when the universe was less than 1 billion years old, implying either that they formed from massive seed objects very rapidly after the Big Bang, or that they accreted material at rates far exceeding what standard models allow. As we pull back now from individual objects, from icy dwarf planets to extreme stars to the collapsed remnants of stellar lives, a larger pattern begins to emerge. The universe is not a static collection of objects. It is a dynamic system in a particular phase of a very long history. The epoch we inhabit, roughly 13.8 billion years after the Big Bang, is what cosmologists call the Stelliferous Era, the Age of Stars. Galaxies form, stars are born from molecular clouds, burn their fuel and eventually die, seeding the interstellar medium with heavy elements that become the raw material for the next generation of stars and for planets, and in at least one case, for the chemistry of living things. This era will not last forever. As galaxies consume their reservoirs of cold gas, the rate of star formation will decline. The most massive stars will burn out first within millions of years. Sun-like stars will persist for billions more, the smallest red dwarfs, burning hydrogen so slowly that they may live for trillions of years, will be the last stellar generation to fade. After that, the universe will enter a long twilight dominated by cooling white dwarfs, dead neutron stars, and the occasional black hole. The timescales involved in these later eras are so vast that they can only be rendered in powers of 10. The last white dwarf is expected to cool to a black dwarf. a dark, cold remnant in roughly 100 quadrillion years. Even then, the universe will continue to evolve. Quantum processes will slowly disintegrate ordinary matter. Black holes evaporating via Hawking radiation will complete their slow dissolution over timescales measured in googles of years, and then perhaps only the expanding darkness remains. But we are here now in the Stelliferous era, at the moment when stars still burn and planets still form and water still flows on at least one small rocky world. The universe will not always be as it is tonight. The objects we have visited on this journey, Eris and Sedna on the edges of our own solar system, Nu Scorpii with its 7 gravitationally tangled stars, R136A1 burning at the edge of what mass allows, and the neutron stars and black holes that mark the final chapters of stellar lives are all part of the same continuous story. Matter forming, burning, scattering, reforming. A cycle that began with the simplest atoms in the aftermath of the Big Bang and has produced, after more than 13 billion years, systems of such variety and strangeness that even our most determined efforts to understand them encounter mystery at every turn. We have covered a small fraction of what is known. The instruments are still watching, the data is still arriving, and there is no shortage of objects in the universe waiting to surprise us.